So now we'll continue to look at the analysis of the series RL circuit. In the previous section, you learned how to express the impedance of an RL series circuit. Now let's look at Ohm's Law and Kirchhoff's Law and how they're used in the analysis. The application of Ohm's Law to series RL circuits involves the use of phasor quantities Z, V, and I. Notice that we have bold-faced non-italic letters to indicate the phasor quantities, both magnitude and angle. So the three equivalent forms of Ohm's Law, as you learn them in your DC course, V is equal to I times Z, so the voltage is equal to the current times the impedance, in this case, not just the resistance. The current is equal to the voltage divided by the impedance, and the impedance is equal to the voltage divided by the current. Recall that multiplication and division are most easily accomplished with the polar forms of phasor algebra. This makes handling Ohm's Law easier because it involves multiplication and division then of our three components. So let's look at this example here. We've got a resistor and an inductor in series, 10k ohm, 100 millihenries. We've got a source that is 10 kilohertz, and we've got then a current expressed in the polar form as 2/10, 0 degrees, milliamps. So what we need to do then is take a look at what we have given here, and determine how we can solve for the unknown. The current expressed in polar form, as I said, 2/10 at an angle of 0 degrees in milliamps. Determine the source voltage expressed in polar form and draw the phasor diagram showing the relationship between the source voltage and the current. So we have the frequency given, but we do not have the voltage. So the first thing we need to do is determine from our value of inductance, we need to turn that into an impedance. Notice in this case, we're given 100 millihenries of impedance. So we can't use that in this relationship. We need to convert it into an ohmic value. So X sub L, the inductive reactance, equal to 2 pi times the frequency times the inductor value. So we take that product and we end up with 6.28 k ohms of resistance. So now we have resistance and resistance. Now put it into the rectangular form. R plus J X sub L gives us our total impedance for this circuit, 10 k ohms plus J, 6.28 k ohms. Okay, and that's as far as we can go with that. Now we need to turn that into the polar representation. So there's our polar representation for the formula for that. With our values now that we have of the resistance and the inductive reactance, then we end up with a value of 11.8 at an angle of 32.1 degrees in a k ohm value. So notice now, unlike a purely inductive circuit, the angle has changed. The angle now for the total resistance in the circuit, the total impedance, is 32.1 degrees, down from the 90 degrees that we would normally see for a purely inductive circuit. So now we can take one of our ohmic relationships, one of our Ohm's Law relationships. In this case, we're going to solve for the source voltage. So the source voltage is equal to current times impedance, and we take the impedance and that we just calculated. We take the ampere, the current relationship that was given in the diagram, and we get a source voltage then of 2.36 at an angle of 32.1 degrees, now in volts. So notice that we don't end up with clean round numbers. We end up with fractional values when we deal with these types of analysis. Phase relationships of current and voltage then in a series circuit, the current is the same through both the resistor and the inductor. Why? It's in series. The resistor voltage is in phase with the current. The inductor voltage leads the current by 90 degrees. So there is therefore a phase difference of 90 degrees between the resistor voltage and the inductor voltage. If we look at the sinusoidal relationship here, then we can see that the voltage for the source, in this case, we have the blue trace, the voltage for as I said, the source, the inductor. We've got the voltage across the resistor, and we've got the current through the resistor. Notice that the voltage across the resistor and the current through the resistor are in phase with each other. The voltage across the inductor is 90 degrees out of phase. So the current lags the voltage across the inductor by 90 degrees. V sub r and I are in phase, the amplitudes are arbitrary. And you're going to see this more when you do your labs and take your measurements on the oscilloscope. You're going to be able to see these phase relationships and amplitudes. Kirchhoff's law, then, KVL, says that the sum of the voltage drops must equal the applied or source voltage. Since V sub r and V sub L are not in phase with each other, they must be added as phasor quantities. So you can't just arbitrarily add the values together. V sub L then leads V sub r by 90 degrees. So the value then would be instantaneous values along the sinusoidal curves. So if we look at the phasor representation, then the voltage drop across the inductor vertically, the voltage drop across the resistor horizontally gives us again that right triangle relationship. So again, we can use our rectangular and polar relationships. Now the source voltage is equal to the sum, the phasor sum or vector sum of the voltage across the resistor added to the J V sub L, the voltage across the inductor. Okay, we can combine them then vectorially using the Pythagorean theorem again, and then the angular relationship for the inverse tangent to get to our polar relationship. Okay, so that's as far as you can combine them together. So the two relationships, again, write this down in your notebook so that you have it handy. Another relationship that we've learned here looks very much like the last one, but now we're looking at the right triangle relationship or the phasor relationship between voltage drops across the inductor and the resistor and how it relates to the source voltage and the angle. Since the resistor voltage and the current are in phase with each other, the angle theta also represents the phase angle between the voltage and current. Notice here now we've got three vectors in this phasor diagram. Again, the voltage across the inductor, the voltage across the resistor, and we've laid on top of it the current then through the circuit, and it is absolutely in phase, you can see, with the voltage across the resistor. Inductive reactance then varies directly with frequency. Like I said before, instead of that pure 90-degree relationship, now as we change the frequency of our source, we're going to change the inductive reactance. When X sub L increases, the magnitude of the total impedance also increases. When X sub L decreases, the magnitude of the total impedance also decreases. Why is that? Well, that's because our relationship said X sub L is equal to 2 pi times the frequency times the value of the inductor in Henry. So it's a direct relationship. It's not an inverse relationship like we saw with the capacitors. In an RL circuit, then, the impedance is directly dependent on the frequency. So directly, not indirectly, not inversely, directly dependent. So just like we saw with the capacitors, we can look at this relationship using the triangle, and we can see as the frequency increases, we've got an increase then in our angular relationship. The phase angle also varies directly with the frequency. So again, to reiterate, as the frequency increases, V sub L increases, that's that axis right there. Z increases, the length of the resultant, the phasor resultant, and the angle increases. Each value of frequency then can be visualized by forming a different impedance triangle. So let's look at an example here. In this example, RL circuit, determine the magnitude and total impedance and phase angle for each frequency. We're going to change the frequency. We're going to use fixed values of the resistor and the inductor. Again, in this case, given in millihenries. So starting off with a frequency of 10 kHz, we run it through our relationship, we get 1.26 k ohms of resistance for that first frequency. Now we take these values, put them into the polar conversion. We do the polar conversion using the Pythagorean theorem and the inverse tangent, and we get an impedance of 1.61 at an angle of 51.6 degree k ohms. Okay, so that's at 10 kilohertz. So let's increase it now to 20 kilohertz. Do the same route here. Calculate X sub L. Now we get 2.51 k ohms. Put it in the conversion formula. When we do that, we get 2.17 at an angle of 68.3 degrees in k ohms. So we went from 161, 51.6 degrees k ohms to 2.7, 68.3 k ohms. Now we're bumping up to 30 kilohertz. At 30 kilohertz, our total inductive reactance is 3.77 kilo ohms. Run it through the conversion. Now we have 3.90 at an angle of 75 degrees in k ohms. So we notice that the frequency increased, X sub L, Z, and theta, the angle, the phase angle, also increased. All because of this dependence on the frequency and as the frequency changes. So when we come back, we'll look at parallel circuits.